Hi class, I'm doing this video to help you understand how to calculate z-scores. A runner from team, a runner for team one. So let's just say that's like the first runner on team one. Ran a race in 59 seconds. Team one has running times with a mean of 64.2 seconds and a standard deviation of 1.2 seconds. A runner for team two, like the second, I guess the first runner on team two, you can kind of think of it that way, can run a race in 57.5 seconds, and team two has a running times with a mean of 62.1 seconds and a standard deviation of 4.3 seconds. So now the first question is which runner is faster? The first runner from team one who ran in 59 seconds, or the runner from team two who ran the race in 57.5 seconds. So the smaller number is the faster time. So the faster runner is the runner first runner for team two. So it's it's the team two person. Okay, that appears to be the faster runner. When we look at just times by themselves, the runner from team two appears to be the faster runner. And then they ask, what is the z-score associated with the running time of runner from team one? The z-score. The z-score is it's always your data value minus the mean divided by the standard deviation. I'm just use SD for standard deviation. Okay, so it's the data value that you're trying to ask the z-score for what data value minus the mean divided by standard deviation. So for this one, it says, what is the z-score associated with the running time of a runner team one? The runner for team one. So the runner for team one ran in 59 seconds. So that is the data value that we're trying to find the z-score of. So I do that, I plug that in for my data value, minus the mean of that team is 64.2. And divide by the standard deviation of that team, which is 1.2. So we okay. Let's see if I can just move this. Okay, so you did 59 minus 64.2. Okay, and I press enter and give number. So I just did the numerator. I did and that's the way when we're doing calculations like this, it's important that you remember that when there's subtraction in the numerator of a fraction, there's like in parentheses there, and there's always parentheses in the numerator and denominator of a fraction saying do all of the operations in the numerator, do all the operations in the denominator, and then you divide the numerator by the denominator, or divide the numerator divided by the denominator. Okay, so that's why I have to do then top subtraction first, then press enter, get a number, and then I do divide by 1.2. Okay, so I get this number, negative 4.33. And that is a z-score for this runner. All right. It says next, what is the z-score associated with the running time for running team 2? So again, I'm going to take the data value. This one was for the data value associated with runner of team 2. So that they say a runner for team 2 can run a race in 57.5 seconds. The mean of 62.1, so I take away 62.1, divided by a standard deviation of 4.3. So I get my calculator. I do 57.5 minus 62.1, negative 4.6, divided by 4.3. Was that the, let's double check that that was the, yeah, 4.3 was a standard deviation. That's a large standard deviation compared to the other one. And I get this negative 1.06. Oh, hold on a second. If I rounded to 2 decimal places, it's 9, so it would make the 6 go up to a 7. So I'd be say 1.07 if we rounded to 2 decimal places. Okay, and then they say, which runner is faster relative to their corresponding populations? So a z-score is showing you how far away, how many standard deviations away from the mean that particular data value is. So pretty much they're telling you how much larger than the mean, how far away this person is from average. And so the larger this value is, then the further away it is from average. So like, here's the distribution. Is what a distribution looks like. If you have like times, like racing times, they usually are normally distributed. So it looks like this. The mean is in the middle. And which would, if somebody has if somebody scores exactly the same, if a runner runs exactly the same time as the mean, then they're going to have a z-score of 0, because they're going to have their data value, which is exactly the same as mean, and they'll have you'll have a 0 in the numerator here. So they'll be right at the mean, which is in the middle here at 0. Then somebody that's below average, and right where this this mountain is halfway down, or is called the inflection point, is at 1 standard deviation below the mean. And then this would be like, I have to keep these tick marks approximately the same amount apart, and so on. So somebody who's negative 1.07 below the mean is not that far away from average. They're just they're just 1 standard deviation away from average. But this person at 4, they're 4, look, they're 4 whole, in their distribution. I mean, these are 2 different distributions. So I should technically, I should draw for 2 separate different distributions. One for the distribution of the team 1, because it has a mean. The mean of team 1 was like the 64.2, and a standard deviation of 1.2. And then the mean of the second one was 62 with standard deviation of 4. So when we look at z-scores, the z-score is comparing that person to everybody else on the team. And this person is very, very low. It's 1, 2, 3, 4, over 4 spaces below the mean, meaning that this person's a lot faster than everybody else on the team. Because everybody else is where this high mountain is. Everybody else's times are where the high mountain is, and they're way out here. And when we compare that to this other person, they're only 1 space, 1 standard deviation below the mean. So they're pretty close to the scores that everybody else, because they're pretty high and close to this high mountain part of this picture. So their just score is not very far away from the mean, and not very many standard deviations away from the mean. So he is kind of a regular runner. He's a typical runner for that group. So which runner is relatively more which runner is faster relative to their corresponding populations? Well, it's from team 1. And that's because they have a larger, you just look at the z-score in absolute value. So I'm ignoring the negative. Whichever one has the larger z-score is the more extreme one. And when someone has lower times, the lower z-score, so then that means they're a faster runner, right? Someone with a positive z-score here would mean that they're above average. Their length of time at the race was above average, which would mean they're slower. So the smaller z-score is the negative 4.33. And you have to remember here that the larger negative number is actually smaller than, so negative 4.33 is actually smaller than negative 1.0. But the way I like to think about it is like that if just look at it in absolute value, the one that's farthest away from the one in absolute value that has larger z-score is further from normal. In this case, they are really below normal. And because of the negative z-score, they're below normal, and they're below the normal typical time. That means they're faster runner. All right. I hope that you found this valuable. Have a great day. Bye.